G'day chemistry students. In this video we are looking at dot point 8.1.1 and 2. Our focus is going to start to really veer into the monitoring and management of the environment. So already we've been looking at different techniques to identify unknown substances, and that could be used for environmental analysis. But carting around expensive spectroscopy equipment, these big boxes and machines that don't really get moved anywhere, and certainly are very expensive, are not always the best way to be able to identify unknown substances. So in this video in particular, we're going to be focusing on reasons why we need to monitor and manage the environment, but in particular really start to hone in on looking at some techniques that can be used, which are cheaper, more mobile, etc., to actually be able to do some analytical chemistry outside of a laboratory. Let's get into it. So when monitoring chemicals in the environment, it's really important for us, as we said before, to figure out what the chemical composition of a particular substance is, or the contaminants that are present, and identify them, and then possibly as well also figure out what the concentration of those contaminants are too. That may require us to look at water, soils, or the air when monitoring the environment itself. So when looking at inorganic substances in the environment, they certainly have their place, but in particular, when we have large concentration of contaminants that usually wouldn't be there, we find that they have damaging effects. So for example, a damaging effect might be silver ions. If we end up dumping chemical waste somewhere that has a lot of heavy metals, in particular silver, that's quite toxic for aquatic life, both in fresh and saltwater conditions, and may end up completely destroying aquatic ecosystems. On the flip side though, carbonate ions can be really important in waterways because they can regulate and buffer acidity in those places. So definitely there is a time and a place for different organic substances. What we want in places and how much we want, completely dependent on the substance and its behavior. So I guess as responsible scientists who are conscious of the environment and the impact that we have, we need to be really careful about the substances that we use and where they end up after they've been used in scientific and chemical processes. So there are lots of different types of tests that we can use to try and identify what inorganic substances are actually present in some of our environmental samples. So using our knowledge of different kinds of reactions and how they proceed, there are a bunch of tests that we can use to be able to distinguish between different types of inorganic ions. So for example, precipitation reactions, based on our knowledge of solubility, as well as potentially some knowledge that we may have around the results of particular precipitation reactions. For example, the color of precipitate that's being made. We may be able to do some tests where we can identify ions either by the formation of precipitate and or the color of precipitate that is made as well. This precipitation concept can be taken a little bit further, and we're going to be unpacking a new concept, which is the idea of complexation in this topic. And that complexation concept can take what we already know about precipitation a little bit further and allow us to develop some more robust testing practices. In a lot of cases as well, we can do some flame testing and test for the presence of different kinds of ions by burning those metal ions and enabling them to release the characteristic colors of each of the different metals. So in these activities that we're doing around chemical monitoring and testing for ions, we're going to be identifying a certain set of cations and a certain set of anions. They're listed there. When looking at the cations that we're testing for, we can use a table like this, which has been constructed based on the idea of solubility, so precipitate versus no precipitate, but also has data which relates to the color of precipitate that's formed when these cations react with a certain set of anions. So for example, for these cations, they generally don't form precipitate with chlorides, except for a couple, lead and silver. For sulfate, it's a very similar story, but then we begin to bring in barium sulfate, for example, as a precipitate. And most of them will react with hydroxide and form a precipitate. But what we'll start to notice is that there is beginning to be a little bit of difference in the color of the precipitations which are being formed. This can be really useful in being able to quite quickly distinguish some of our unknown substances. For example, if you put copper together with hydroxide, you're going to end up forming a blue precipitate, which means if you have an unknown substance, you combine the unknown substance with a hydroxide and get something that's blue. Pretty good chance that the contaminant that you are looking at that stage is copper. In some instances here, though, within the table, we can see that there are circumstances where we may not be able to distinguish between ions. For example, if we have calcium and magnesium reacting with hydroxide, we may end up finding that they both produce a white precipitate. We could then try and distinguish and figure out whether or not they react with sulfates and chlorides. If we find that they don't form a precipitate either, then it may be really difficult to figure out whether or not we're working with calcium or magnesium. However, we could use flame tests as a way of distinguishing between the two. So for example, if we had a calcium contaminate, if we were to burn that substance, we would find that we get quite a characteristic darker orange color in our flame. Compare this to magnesium, which you won't actually find on this color chart because magnesium compounds or ions don't actually produce color when burnt. Therefore, we wouldn't expect to see any positive flame test at all. When testing for anions, we will go through a series of tests, including precipitation tests. But in this circumstance, we can actually undertake something called a complexation reaction to further distinguish between some of our ions. To understand a complexation reaction, we probably have to first understand what a complex is itself. Essentially, it's a metal atom which is bonded to a set of what we call ligands. So all of these waters coming off our copper in the center, we would all call ligands. There's a covalent bond between each of the ligands and the metal in the middle. In particular, this type of covalent bond is a coordinate covalent bond, not something that we really need to understand inside and out for the purposes of this module, but maybe something that you might want to read into yourself. This forms, in this case, so copper with 6 water ligands, forms hexa-aqua-copper 2. So hexa referring to the 6, aqua meaning water, and copper being our metal in the center. The Roman numerals indicate that the charge of this complex is +2. So this actually forms hexa-aqua-copper whenever we dissolve copper into water. Some metals, in particular transition metals, like to form these complexes and will generally do something like this, even though there may not be 6 waters, the number of ligands may be a little bit different. But this happens a lot for transition metals when they are dissolved in water. You end up with these ligands of water surrounding it and forming some sort of charged substance. Because it's charged, it does make it aqueous as well. Note as well that we can write complexes using square bracket notation, and we always indicate the charge on the left as well. However, there's some interesting reactions that can start happening with these ligands, and again, we call these complexation reactions. The ligands can be substituted in a chemical reaction and change the solubility of a complex. So for example, if we were to have copper dissolved into water, remembering that previously we would usually just write copper dissolved into water as Cu2+. Now we're recognizing that it's a copper complex, hexa-aqua-copper. If we were to react the copper with hydroxide, we would then form copper hydroxide, something like this. Put a 2 out the front to balance it. That's something that would be pretty common to sort of note how precipitates or solids will form. But note when we're taking into account the idea of this complexation process, that the complex itself actually changes. So we still pick up 2 hydroxides, but they're actually replacing 2 of the waters. And you might be able to see the action of what's happening in the complexation reaction, the substitution or changing of the ligands in the diagram on the right. Here we have hexa-aqua-copper, 6 waters all the way around. We add our hydroxide ions. We keep 4 of the waters, and the hydroxide groups replace 2 of those waters. That forms tetra aqua dihydroxy copper. Formula down below. And this is insoluble, this complex, and ends up forming a solid. So it's still very similar to the copper hydroxide that we've talked about before. But again, we're adding these concepts of ligands, and that is slightly changing the formula despite the result not changing at all. What's interesting though is we could take something like our tetra aqua dihydroxy copper and add something like ammonia into the mix. So still have a water-based solvent. We've added a little bit of hydroxide, got this solid precipitate that's existing and is separated from the aqueous substance. But by adding ammonia, what we have is ligand exchange. Again, this idea of ligands being able to be substituted in and out. So the amines are going to come in and remove both of those hydroxides as well as 2 of the waters, forming tetraamine diaquacopper. Now we have 4 amine groups and 2 water groups. Again, this is soluble, no longer insoluble, effectively meaning that in the 2 steps that we have on the left, we form a precipitate, add ammonia, we have a complexation reaction that changes the ligand up again and makes the resultant substance soluble again, effectively removing the precipitate. And this is where some of our anion tests will get really interesting, because we will end up forming a precipitate and then undergoing another complexation reaction, generally meaning that we're adding ammonia, to then remove that solid and reverse a precipitation process. This is quite a special process. Not all anions are going to be capable of allowing this to happen. And because that's quite selective, that's the reason why we're going to be able to distinguish between different anions when we do our anion tests. This table here is probably a little bit more complex than the cation one that I showed you before. You can have a quick read over of it if you want. We might focus on looking at that in a little bit more detail in class. But effectively, what all of our known information about complexation reactions, precipitation reactions, and flame tests is going to actually allow us to do is create flowcharts to be able to test for unknown ions. So for example, this one over here is a flowchart that we can use to test for the presence of different cations, and the one over here could be used to test for the presence of different kinds of anions in an unknown sample. These may not necessarily be the flowcharts that we follow with. They're just examples. We might, at the very least, try and design a method for the cation one that's a little bit easier to do. We'll see whether time will allow us to design a slightly different flowchart to the one that we've got over here when we do our anion tests. Thank you very much, everyone. In the next video, what we're going to be focusing on is inorganic spectroscopy techniques, essentially using these to construct what we call calibration curves, and using those calibration curves to determine the concentration of different samples. But until then, have a good one.